So one of the things I like about physical science is it's very consistent across the board, across all disciplines. So we have this conservation theme, conservation of fill in the blank. So of course you may have heard of conservation of energy. Energy can be transformed from one type of energy to another type of energy, but it's always conserved, which is great for folks who want to do experiments because you can track it. It didn't just disappear. There's conservation of matter. We count on that a lot in chemistry, that actually the atoms you start with are the atoms that you end with in ordinary chemical reactions. Matter is conserved. Conservation of momentum. Remember we said that momentum is mass times velocity. And that was one that I believe I might have said that the momentum of a Mack truck is greater than of a bicycle. Okay, so now momentum needs to be conserved. So for instance, if one object crashes into another object, okay, that energy, that momentum needs to go somewhere. It can't just disappear. It can be converted into other things and transferred to other objects, but it doesn't just disappear. Another important player in, actually, when we talk about the formation of our solar system, is this conservation of angular momentum. Now, angular momentum is similar to regular momentum, but angular momentum deals with either rotating objects or orbiting objects. Okay, so the conservation of angular momentum. I just am excited that that we can crunch numbers and track these things. Conservation of a lot of quantities in physics. So focusing on what is angular momentum? So I said angular momentum was if something is spinning or rotating. So angular momentum is, okay, the mass times the velocity times r, the distance that the rotation or the orbit is occurring. So for instance, if we just talk about something having kind of orbiting, and we could go ahead and make this, the Earth orbiting the Sun. And so here we would have the mass of the Earth, okay, the velocity it's going, direction it's going, and then the radius would be here. Okay, this is the distance between the center of motion and the Earth. Okay, so now what this says is that, I'm going to show you an example of a skater here in a minute. Can you see where if angular momentum is conserved, that means it cannot change. It means it stays the same. Okay, can you see where if, for instance, r becomes smaller, okay, if r becomes smaller, you can't change the mass. So what that means is that velocity will increase. Okay, an example I chose, if r becomes smaller, then the velocity must increase. So if you think back to the Olympics, watching skaters, that's exactly what she's doing. So as she sets herself a spinning motion, she applies a certain amount of energy and gives herself a velocity, and so she has angular momentum as she's spinning around. So as she spins with her arms extended, she has a large R. I'll just say big, a big R value. Okay, that's her radius. Okay, and then notice as she brings her arms in, okay, she makes her radius smaller. Small radius. My R's look like my V's, don't they? So with the smaller radius, notice what happened to her speed. Faster velocity. Okay, so that's kind of how that goes. So actually, one more thing then. Over here we have a planet orbiting the sun. And one of the things that in Kepler's laws of motion about planets as they orbit the sun, remember it was the second law, right, that said that here at perihelion, okay, it goes fastest. So what do we have at perihelion? At perihelion we have a small r, okay, and that means a large V. Here at aphelion, okay, we have a large R, large radius, and so that means it's going slow. Okay, so actually this is consistent with what Kepler's second law, conservation of angular momentum.